So thanks for everyone for coming. I know that today of all days, it's not the easiest for people to get away with the JWST deadline looming. Aaron suggested I put a clock up there, a deadline clock, so you can see every second tick away. We are not so cool, but really, we appreciate you guys coming. We've got, I think, what are going to be two exciting talks today, and I'm going to go out and let them take over. So the first one's going to be by Peter Melchior, who's also going to give us a colloquium tomorrow. And so we'll let him jump into his talk. And I just want to say in advance, keep your eyes peeled for what he's going to talk about tomorrow. And then also we've got some slots left in his schedule. So if you're interested in chatting more with him, to please do so. So with that, QR code's going away. Thank you all for signing in. Peter, all right, feel free to take it away.
Thanks much. Thanks for the invitation. It's my first trip to UVA, so happy to meet all of you, or as many as we can fit into 2 days. So today I will talk about spectra and time series, and tomorrow I'll be talking about imaging primarily. So we'll cover all bases. And I'll treat the spectra and time series in a very similar way in one part, because the techniques we're using for them will be quite comparable.
Is it coming up?
Do I need to reshare?
Yeah, you can reshare your screen, then it should come up.
Okay. How's that?
Perfect. That looks good to me. Good online, Pratik? Great.
All right. So we're doing spectra and time series today. They will work in a very similar way. And if you're surprised by that, both are one-dimensional time series and they're ordered. So there is kind of some similarity between them, just kind of from a structural perspective. Right. A lot of what I show here is motivated by my department's very active participation and building the prime focus spectrograph. Already it's actually installed at the Super telescope. It's going kind of through various phases of getting kind of fully science ready, but it's kind of it's an instrument. If you're familiar with DESI, it's very similar to DESI. It also has several thousand, in this case 2,400 actuated fibers, but it is on an 8-meter mirror, so we can go deep very well. And galaxy evolution is one of the primary galaxy evolution and cosmology are one of the primary targets. The third survey is galactic archaeology, so Milky Way stellar population studies in detail. So for galaxy spectra, from a data-driven perspective, they are a little bit awkward to deal with because redshift moves all of the features. So if you think about a sort of a standard neural network, fully connected neural network, then you would like all of the features to stay in place. Actually, you almost demand it just by the structure of the network. And the fact that they're moving is a problem. But that shift, we all know how to mathematically describe that shift. So I don't need a neural network to figure out what redshift is. I will impose that, show you how. What I want a neural network to get to is all of the features in the rest frame spectra. So what you see on the left-hand side is a change in one dimension of the latent space that we are going to construct. And you can see that that dimension largely is associated with the transition from quiescent to starbursty galaxies. So it's kind of the dominant direction in that latent space that's going to emerge. Not surprisingly, that's sort of the dominant feature in galaxy spectra. What are we going to do? We're going to sort of acknowledge the fact that there's sort of two different independent degrees of freedom. There's the redshift and whatever latent variable, think of this as a spectral type. As that I want to have a decoder that from that spectral type gives me a rest frame model, and then I'm going to use the redshift and an analytic redshifting operation. We're going to resample that on the observed grid of our spectrograph, and that is how we get a observed spectrum. To make this an autoencoder, an autoencoder is a combination of an encoding architecture with a decoding architecture. It's called auto because the spectrum on the input side is supposed to be, reconstruction is supposed to be identical as close as you can to the spectrum on the input side. So we have an encoder on the input side that tries to get to these latent variables. So it tries to recognize the spectral type. How does it do that? Because it's not obvious how you would actually do this. So this is a little bit of a more kind of detailed look on this encode and decoder architecture. The decoder is very simple. It's a fully connected neural network because in rest frame, all of the features stay where they are. I'll change the type, I'll change the features, but say oxygen 2 will always be at the at their respective length. So I can use a fully connected neural network, and that just generates these things. It's very simple. Encoder side is harder because if I go back, you need to be able to identify the latent variables of the rest frame model from the observed spectrum. That means that stuff is moving about. That's not trivial. What we are doing here is we're using an attention model. And attention is a very common neural kind of element of an architecture where you can basically search for a certain kind of feature to exist. It's effectively a data-driven filter. And if that feature exists, the attention will sort of take note of it. And that's what we actually need here. So we basically think of this as scanning for different line shapes and different breaks across the entire spectrum. And when they are present, regardless of where they are, when they are present, that information is communicated into this latent information. So effectively, what we are doing is something very traditional, namely identify the spectral features, and the accumulation of spectral features is characteristic of the rest frame. It's a sort of can be summarized as the properties of the rest frame.
Can I jump in?
Sure.
So so there's two things, right? There's the redshift that we understand mathematically, and then we have this other S factor in your little animation. Could we go
Yep.
back?
Yep.
Yes, so physical spectra. So right, so the spectrum, especially when you get more star-forming galaxies or star-forming activity, the line ratios depend on the star formation rate and the metallicity, right? And so even in the metallicity field, right, there's still different diagnostics that try to use the line ratios to get metallicity, and there's all this discussion and so forth. So here it seems like you found a way to have this very kind of S4 number that somehow is able to kind of beautifully, reproduce the whole continuum.
Right.
Is that now data driven, that S factor?
Yeah.
Or is it something that was designed for this training set?
And there's no need. So this we'll see that the latent space that we're constructing is actually 6-dimensional, and one should say just 6-dimensional, because the input spectra, this is Sloan, so this is kind of 5,000. The vectors is about 5,000 elements long, and the compression goes down to 6. And in fact, like 2 dimensions would typically do it. For everything that isn't an active galaxy, 2 dimensions would be just fine.
Yes, exactly.
But what these dimensions mean, I don't impose anything so far. We'll get to what we can impose, and I'll show you what to do, but this is completely data-driven. Yes.
So this is S4s out of the 6, right?
Yeah, exactly.
Okay.
Out of 6.
Next.
So let me move on. And so the main part here is this attention model. You may have heard about this as a type of architecture in the transformer, for instance, they use attention, but you can use just this bit. This is not a transformer. It's just kind of a piece of a kind of a more complicated architecture that we can use. And what it does is essentially a very sort of an extension of a matched filter approach. It finds both the filter shape and the signal in sort of in the same way. But what it then does is it sort of encodes that into the latent, and it's a summarization of all of the features it did find. And that's a very useful thing for Spectra to have. So let's look at the spectrum model we're constructing here. And you can see these are 3 examples. You can see that I've indicated the lines, and it works just fine. This is 6-dimensional, but I can, apart from the last column, which has some kind of outflow part of it, you can see some line asymmetry here. Apart from that, we could do this. The first 2 we could easily do with 2 dimensions. The compression is incredibly radical if you think about it. But it also tells you that spectra are not, like the fundamental space of spectra is not so high dimensional. It is highly compressive, and that's okay. This is why this works. You find a few interesting features. For instance, here, it predicts the existence of a line in the rest frame. It predicts the existence of a line that didn't get observed because it's too blue. And it does that because it has seen a very similar spectrum at slightly higher redshift where the line is observed. So now you get a model over an extended rest frame range because you expose the bluer sides by going to slightly higher redshift. We do assume implicitly here that there's no evolution, and over the course of the Sloan spectra from redshift, say up to about half, there isn't a whole lot of galaxy evolution happening. So the assumption is quite fine, but it is an assumption. We have robustness to kind of features like this. This is a residual of the skyline subtraction. It just kind of ignores. And we follow the different line shapes that you can find here, kind of in the kind of H alpha region. You can see the kind of different line shapes appearing both in absorption and emission. So this works. And again, compressed down to 6 numbers. Here we're doing something even more radical. I decoupled the decoder and made the decoder use twice as many spectral elements as the encoder. So we're internally oversampling. And what you can see here is we can resolve in a data-driven way the oxygen 2 doublet, which you cannot do in SNP because the line spread function is too wide and the resolution isn't there. And I measured that the lines that are kind of the line shapes and line strengths that you get are identical to the S2 doublet, which is what you expect in theory. But this, these aren't just there, right? They also have the right heights. So let me move on. We can go beyond that and actually look at the latent space distribution. Right? I just said that it exists, it's 6-dimensional, but what does it actually have? And I should point out that we do something unusual compared to the majority of the machine learning literature. We do something unusual here in that we are not using a variational autoencoder. Variational autoencoder is a version, sort of, if you hear autoencoder these days, it's almost universally what you imply is a variational autoencoder that has some benefits. What that does is it requires that the latent variable here has a Gaussian distribution. Nothing in this problem like demands that there's a Gaussian distribution and it turns out not to be necessary. We do something else instead. We take an input spectrum and artificially redshift it. We know what the operation is, so we might as well. And then we encode it again. And I want that the place where it gets encoded again is actually the same as the original version. What I'm inducing here is redshift invariance. So I want very explicitly that my rest frame position only refers to the spectral type, but not to the redshift. And I can impose this as part of the training losses. And then I get a distribution that is not Gaussian, and I will capture that distribution with a different neural architecture and normalizing flow. That's just a technicality in this way, right? I can totally live with this distribution. I don't care. But we're going to want to evaluate, for instance, how likely a certain spectrum that I've encoded is. And I need to evaluate the probability of this sort of ragged-shaped distribution, which I don't want. And it's easy to map that onto a Gaussian. Here, in this case, a 6-dimensional Gaussian. So I map this position into this Gaussian, and I can easily evaluate how likely the sample is. We're going to use it for outlier detection in a minute. Let me talk a little bit about these losses, because since we are sort of an ML-focused seminar here, it's not a variational autoencoder, so it doesn't have this KL penalty. That's a divergence from a target distribution, which is almost universally used as a standard Gaussian. So you'd like to have a distribution that looks like in latent space that looks like a Gaussian, but there are problems with this. There's no reason why this needs to exist. I can go into depth why people use this and why it's so commonly employed. But it's just not necessary in this case. And we replaced it by this consistency loss. This is where we make this augmentation. So we change the redshift and we just force it to be at the same place. And kind of, we also have another penalty that says that if something is different in the original space, so in the space of the spectrum, then it should also be different in the latent space. And that's kind of this other penalty that we add. What that does is it prevents the mode collapse. So it needs to have because there are different spectra in the data space, there are also different positions in latent space that need to be populated. And that things that are similar to each other actually end up clustering in the same place in latent space, and that encourages clustering. Nice.
So the data, maybe you said this, the data, aside from the augmentation, the data themselves at this point are simulated data, or they're real data?
Nothing got simulated here.
All real.
Yeah. We've tried it also with Boston, with DESI, and but it's optical spectroscopy, ground-based variety, but nothing is simulated. So we don't know what we are doing here in essence, right? We're just describing an empirical model for the spectrum. Here, this is the first time when we actually try to do this kind of try to understand the physical properties of what we see, and that is, so we ask in latent space, this is a 2-dimensional projection. It's a UMAP projection, if you know what that is. It's a 2-dimensional projection for visualization purposes only of the 6-dimensional latent space. And what you can see is that there is a very strong ordering in that space. You can see that there is redshift ordering. If you're confused that we have dependence on redshift in the latent space, despite making it redshift independent or invariant, that's a selection effect. That is, at high redshift, you find the big quiescent elliptical galaxies, and these are the ones that you see on this edge. And the faintest ones, the most nearby ones, they need to be here. They need to be the smallest ones. They need to be at low redshift because otherwise you can't see them. So that's the effect you're seeing. But other than that, the ordering is largely mass and specific star formation rate. There's also, here in this, we also look at dust attenuation, for instance. So you can see the dusty galaxies are in the interior. So this latent space actually knows something about the properties of galaxies that we would have recognized by traditional spectral analysis. We can effectively just go into a latent space and estimate the properties of these parameters without doing spectral analysis at all. Now going to kind of outliers and asking the question of, okay, what happens if we ask for the probability of these samples? So we kind of encode all, this is now DESI, we encode all of the spectrum. We have this latent space, again, 6-dimensional. Now we ask the question, which of the samples from DESI are sort of unusual? They end up in places that are kind of really out in the fringes of the distribution. What we see is there's a bunch of stars in there. In the DESI galaxies, they're not supposed to be there. These are not just targeted as galaxies. The pipeline thinks that's a galaxy, but it just isn't. That's kind of 2 stars on top of each other. That's just 1 star, and you can clearly tell that is a stellar spectrum. It's a beautiful spectrum. And obviously in the galaxy population, that's an outlier. My favorite is this one. It's a broad absorption line quasar. You can see the kind of massive dips here. I can't see this, but I think that's magnesium too. You can see the massive absorption. Not many of these quasars are known, and we just in a way accidentally and automatically found this. We didn't like search it specifically for that. It's just it is unusual. We asked also the question, okay, what can we do with these infrared properties? What can we do with these latent spaces? And one of the questions that we recently asked is whether we can predict infrared properties of the same galaxies of the optical. And that's supposed to be not doable, because if you look at mechanistic descriptions of the optical and infrared spectrum, the contributions to the infrared is typically pars, so dust, and AGN contributions, and they have just no power in the optical. That's kind of the spectral template. So from prospector, there's just no effect on the optical. So they should be completely decoupled, and it means that by knowing the optical part here, we shouldn't be able to predict the infrared part. You can probably guess where this is going. We totally can. So here's an optical spectrum. Here is the WISE photometry, which we are predicting from the optical spectrum, and this totally works. So the separation between the optical and the infrared cannot be as strong as it's implied by these mechanistic models. What's a little bit weirder is that if you try to predict the same, if you try to make the same sort of physical prediction with Segala or Prospector, which are both physical SED models, then they will actually fail. So these are the data points. And that is the spectrum reconstructed on the optical. So we're basically extrapolating from the optical to the infrared, and it doesn't have coverage there. It doesn't actually get up to the data. That's a concern. We're using Prospector or other SED models, and you're sort of in the transition between the optical and the infra, which for James Webb you often are. That is a bit of a concerning problem. The fact that these are decoupled in ways that real galaxies aren't. One should be sort of bothered by that. I'll jump over this for the sake of time, because I want to go a little bit further. We're applying this also for kind of exoplanet spectroscopy, where the redshift in this is just the kind of the Doppler shift that is induced by an exoplanet. It's a very simple problem. I don't have the time to get into this because I would like to move to the time series part. The time domain astronomy is obviously what's driving a lot of this, but in astrophysics, we have evolving systems all the time. So think of this, if you're not in time domain astronomy, but you're kind of dealing with evolutionary processes of a different kind, what I show you still applies. But you have problems like this. You have some data, it's irregularly sampled, that's different from spectroscopy, but it is still time ordered. And have multiple channels. And what you'd like to know is you would like to have sort of an empirical model for the shapes, for instance, for the emission of a supernova once it went off. You would like to know that if you see some of this, what type of supernova is that? Do we need follow-up? What do we do with this? And so the question is kind of what do you do when you see something like this? There needs to be fast classification. You would like to know something about the type of object that has just gone boom. Okay. So we're doing something very similar again. We're using an autoencoder. Now what we are encoding is the full trajectory, so the full time series of whatever data we have. We're going into some latent space, we're decoding it again and get the reconstructed trajectory. So everything here looks exactly as before. But there's one trick here that we're using, because we lose the sort of the rigid structure that the temporal spacing is irregular. Whereas in the spectrum, right, we had this regular kind of regular sampling. There might be some kind of spectral elements missing, but other than that, they're sort of nicely ordered, and then you know the spacing. In order to augment that, we need a model that holds these kind of irregular time samples together. And what we're using is we're pretending that the time series comes from an ODE. So we posit that there is a system that is described by an ODE. I don't know what the differential equation is, but there's some evolution equation that tells me how this temporal signal should evolve. And if I find this equation, I can evaluate it at any time. So T here is sort of some abstract time that is not limited to the times when I got to observe the system. So I have sort of a continuous description of the time series. So if you try this has been done before. If you try this, then you will find that it doesn't fit particularly well. So models that try this with a direct or, again, a variational penalty in this latent space, they don't fit well. So what you can see here is the reconstruction loss, and this is a neural model, a neural network not training well. If you add something instead, if you add a time invariance penalty, if you say that, okay, I want my representation in this latent space to be time invariant, the same way we've done it just with redshift invariance in this latent space. If I want to have this position in the in this latent space not to evolve with time, then your training becomes much more regular. So this is the kind of our new method. It fits significantly better. Low is good in this. This is reconstruction error, so kind of low is good. It trains very effectively, and it has significantly better long-term predictive capabilities. So if you try to do this with a variational autoencoder, you get you learn from the black dots and you predict what is in the future. You said this is a standard this is a damped harmonic oscillator, and you can see it spirals out of control in ways that the data don't. And if you use kind of our model for that, you can see it has like very nice, stable, long-term behavior, which is very difficult to achieve in these neural ODE models. And the latent space, again, has very interesting structure. This is trained on the predator-prey model. So it has 4 coupling parameters of how the sort of increase in prey number is sort of increasing the predators over time, and then there's negative feedback. So these are the 4 coupling parameters. And you can again see in latent space, these are highly coupled. We didn't impose that, so the model didn't know what alpha, beta, gamma, and delta are when we trained it. You can see the latent space sort of picks up on it. And that means that I can actually run inference of that. I can ask, like, how much do I know on these 4 parameters plus the initial conditions? So there's 2 initial conditions for the 2 species number at the beginning of the time series. And I can effectively deduce them from the location in latent space. Right. And so this is a model structurally very, very similar to spectroscopy that you can use for a kind of time series with the irregular sampling, and it can be stably trained. Let me just kind of at the very end jump to kind of one thing that I'm alluding to here, because we've used this architecture also in a case where we don't look at kind of a natural system or an astronomical system, but on neural networks themselves. One of the problems that I've mentioned earlier is that training of neural networks can be finicky. Sometimes you get training behavior that looks like this. This is often a situation when you have multiple losses in your overall loss function, so multiple terms in the loss function, and they start fighting against each other. So in here, it's the variational penalties, and in the standard loss, it's the variational penalty fighting against the reconstruction loss, and you can't find sort of a happy balance between the two. So there's an optimization problem, specifically multi-objective optimization. So we thought, okay, the losses here are effectively just time series as well. So what if we learn an ODE for the evolution of neural network training? And there's no theory behind that, right? And I don't need a theory because it's an empirical model. So I might as well just try to do this. And specifically what we tried here is, here's the training loss. Here's the validation accuracy. So this is what you're trying to actually be good at. Good is high is what you want. And we also varied, as one does, the learning rate during this. So that's basically the speed with which your optimizer operates. That is what you normally do in kind of hyperparameter searches when your neural network doesn't train well. You sort of vary the learning rates and you vary kind of different aspects of your neural network in order to understand how to make it fit well. And what we said is, okay, let's just store all of the results that we have. This is quite common. People track this anyway. So let's just store that and make an empirical model for how it trains. How does the optimization actually respond to sort of changes in the learning rate? And normally you only look at the endpoint of this, but you don't look at sort of how it evolves. And we make a model for the evolution of this. So got a bunch of training runs at the same network, just trained under different conditions with different losses, maybe in different initializations. And we built a latent ODE model out of that. And now, when we want to train the actual model that we really want to get good at, we have some kind of loss at some certain time. We have some learning rate schedule that we started with. We encode that into latent space. We make a small scatter operation, so a small perturbation around this place. And then we predict the future losses and learning rates and validation accuracies of that neural network. And we just pick the one, so the version of this that has the best loss. Sounds simple, right? I don't know anything about the internal structure of the neural networks that I'm trying to optimize here. I'm just looking at its performance. If you do that, you get learning rates that are pretty unusual. They often have very high spiky phases and then drop down to next to nothing. That's a two-phase optimization that deals with the fact that you try to find these very, very shallow minima. This is kind of a visualization of the landscape of the neural network, a deep neural network. And you're often stuck in these kind of very, very rough basins and kind of and like local minima that you don't want to be in, because it's really difficult to find them and then to optimize within them. So what you want is you want to have a smooth basin that's so well connected and has kind of deeper basins within that you want to settle in. And then so you would like to have a two-phase optimization where you go with a really high learning rate, very, very fast step sizes. You go into kind of you find a smooth basin. Then you drop down, you reduce the learning rate so that you can settle into the minima in these bigger basins. And that's empirically much better. And so to demonstrate that this actually works, here's the test accuracies. Red is our new approach, a new schedule. And you can see that we are beating competing schedules across the board for a range of different network parameters and different tasks. This one is a language prediction task. And it gets better the more complicated the surfaces, then this load scheduler is getting better and better. I'll stop here. I know that kind of I jumped over a bunch of things. I'm happy to kind of can respond to questions, but otherwise I take your time away. And I'll just mention that if the spectrum encoding and time series encoding is your jam, then talk to me, because I have two postdoc positions in exoplanet, exoplanet spectroscopy and exoplanet detection, where we are trying to combine these two, spectrum encoding and the time series encoding. And I'll stop here. Thank you.
So I'll encourage you guys to switch over to screen share. If there are any questions either online or in the room, happy to take them now. And I'm going to jump in with one quick one, which is, so thought the sort of spectral reconstruction with SDSS was really interesting, and the extrapolation to Y is super interesting. Can you speak to the volume of the SDSS data that you've been working with, the challenges that poses for training? And then my understanding was that you said you did that with SDSS as you also did it with DESI, and I think the name's not response.
Yeah.
But presumably you did those separately.
Correct.
So can you speak to the challenges that would exist for, constructing a latent space that would encode spectra, even with potentially overlapping wavelength spaces from different signal noise?
So data volume wise, we used, we withheld something like 20% of the Sloan sample and used everything else in the main galaxy sample. And that means that's kind of give or take 500,000 galaxies or so. Training takes an hour. So it's no. It's a really small model, right? These models can be that small because we put some of the physics, in this case, the redshift transformation, explicitly in there. I don't need to train this. And so it's very manageable. Even the DESI data was just about the same. Now, to make a latent space that is sort of that allows you to go from, say, Sloan to DESI to something much higher redshift, for instance. That's not entirely trivial, but for low redshift, it's actually quite simple. We actually kind of trained a different decoder on the latent space from Sloan and predicted the DESI data just fine. And that can be done with the decoder is very stable because it's like rest frame. It's a rest frame decoder. All of the features are very stable. So that was done. I think something like 50 to 100,000 galaxies was easy. So it was very easy to do, just to kind of decouple the encoder and the decoder and train one bit again. So within a relatively, because they have very similar types of spectra, so they're not too different from each other. If you want to do something at redshift 2, it becomes a very different animal because we haven't seen any of the features of redshift 2 galaxy anymore. So tying that together over a wider redshift range is we've tried that. It hasn't worked particularly well. So if you try to kind of do something on a much bigger scale, so for all of galaxy evolution, then one has to tie elements together where you see, say, at high redshift, you see UE features that you don't see at low redshift. So how are they connected? You have to declare that somehow. And I think that will require simulations in order to tie things together in a way that makes physical sense. An empirical model just can't know what you are kind of, they're completely decoupled features. They never rise together. So how should it, there's nothing holding them together.